everyone, welcome to the 6th module. We have already started content based recommender system from 5th module onward, and here specifically we are going to talk about various methods which are used in the case of content based recommendation approach. So, in this particular lecture we are going to see how to use decision tree for content based recommendation. The concept of decision tree we have seen in many earlier lectures as well. So, in today's lecture we are particularly going to build a decision tree from our data set. So, this decision tree induction is a learning algorithm for creating the decision tree where the attributes are all discrete or discretized, and class variable is also having discrete values. So, when you build a tree, you make a structure where there will be root node, there will be branches and so on. The root and the internal nodes are called non-leaf, which are called non-leaf nodes. They basically test various attributes, and as you branch based on certain criteria, you end finally in a leaf node or the terminal node. So, if you follow the path starting from the root and depending on the root variable take a branch, then you can reach the leaf node. And when a new data set comes, once you create the tree, when a new data set comes, you start testing the attributes from which is there in the root node and you continue. Okay. So, this is one example which we already saw. This is a decision tree pertaining to this particular data set. Now, there are 4 features and 1 response variable or 1 dependent variable. So, these are the 4 features and this is the response variable. This is the response variable. So, now the question is, why director has to be there at the root? Why not language, award or type? It appears that this attribute language is not appearing here at all. So, on what basis all these decisions are made? Now, for coming to this attribute selection criteria, we already have known about few attribute selection criteria, and few such we are going to hear for making this split. So, this is the algorithm for decision tree induction. You construct the tree in a top down recursive divide and conquer manner. At start, all the training examples are at the root, attributes are categorical. As I told, if it is continuous, you have to discretize them in advance. Now, example patterns are partitioned recursively based on the selected attribute. The test attributes are selected on the basis of certain heuristic or statistical measure. Now, when do you stop? After all the samples are exhausted and you have made the tree, there is no remaining attribute to be considered, then you stop. So, this is what I was trying to make. You stop when all these examples belong to this class, no. All the examples under this belong to yes and so on. That is your stopping criteria. And you can also stop, these are the 3 different situations. All the samples of a given node belong to the same class. There is no sample left, that is second, and sometimes there is no attribute remaining to explore further. You have exhausted with all the attributes. In that case, the majority voting is employed. Majority voting in the sense, out of all the in that particular set, depending on how many response variables of which category are there, whatever is the majority, you employ it as your class. Information gain as an attribute selection measure, we have already seen that we were using to find out the best set of features for any model. So, now here particularly in decision tree, information gain, Gini index and other criteria, they are used to decide the node and the splitting of the node, splitting of the variables based on the node. Second criteria could be your Gini index. We have last class we have talked lot of things about them, so I am not going to discuss more. Okay. So, now coming to this particular decision tree, we have already discussed how to compute this information gain and how to compute this information needed based on this entropy. So, what we do is we calculate the entropy with respect to D first. As usual, 9 are the yes, 5 are the no, and the formula is sum of minus pi log of pi over all the labels. So, you got this. Now, you got 3 partitions with respect to the variable director. What are the 3 partitions? Because director has 3 values, director 1, director 2 and director 3. With respect to 3, see, look, how many rows are with director 1? 2 plus 3, 5, director 2, 4 rows, director 4, 5 rows and so on. Now, how many yes and how many no also has been tabulated here. Based on that, following this formula for each of these partition, you calculate this entropy value. Once you calculate this entropy value, the total information content, these are the probability of getting this fraction, this is the probability of getting this fraction, this is the probability of getting this fraction, and you multiply it with respect to your information content. And finally, with this process, if you take this information D minus with respect to the director, you get some gain. So, gain here is 0.246, gain here is 0.151. So, if we would like to compare where it is the best, here it is the best. So, that is how in the tree this becomes the root. So, this has the highest information gain. Okay. Now, with making this as the root, what happened? We have now partitioned the data set. In the first partition, we have kept all the entries with respect to director 1, here all the entries with respect to director 2 and director 3. Now, look at the entries related to director 2, here all the elements are yes. So, we do not have to test further, because if the director is director 2, the person is going to like the movie. To remind you, how did we construct, how did we arrive at this kind of data set? In a typical recommender system setting, you find out the item features, then from the rating table, you find out whether the person likes the item or not. That is how you constructed a data set, a complete data set which had all these three group of rows together. Now, with respect to director 2, this person has seen all the movies. So, in future, if a movie comes with respect to director 2, it is going to be recommended. Okay, so moving ahead, here there is no need to go further. So, this is our stopping criteria is met. Now with respect to this one, we are again going to find out the information again. Okay. So now which one? We have now 3 attributes: language, type and award. Now which, with respect to which attribute, that has to find out, we have to find out. With this small data set, we get information again with respect to these 3 attributes. After this, we are not going to do the computation now. It turns out that award gives the highest attribute, highest information again. Now this award, when the award is no, likes is also no. When award is yes, likes is also yes. So our stopping criteria is met. So this part of the tree is over. So here again we have to test with language, award and type. And it turns out that type gives the highest gain. So, and we can see when it is drama type, the person likes the movie, otherwise he does not. So, our full tree is made. Okay. So, now what are the problems in decision tree induction? If the dimensions are very high and sample size is low, then you are not going to get a good tree. Typically, the ratio of the sample size with respect to dimensionality must be as large as possible. If there are noises, outliers and so on, you may also get erroneous result. So, in that context, you need to carry out something called tree pruning that we are going to see shortly. Now, scalability is another issue, because as you saw, to find out information gain, make the partition, you have to consider all the elements in the data set together, all the rows in the data set together. So, if the data set is very, very large, then you cannot feed the entire thing into the main memory. So, as a result, what will happen? You have to have algorithms which will be keeping something in the secondary memory, then taking it back, and this back and forth will be increasing your computational time. So, now for removing these noises and outliers, something called tree pruning is carried out. So, when you build the decision tree and there are anomalies, it will actually overfeed the data. It will not only feed the actual data, it will try fitting the outliers as well. So, under such circumstances, what do? When the tree is growing, starting from the node it is growing, either you stop it in between, do not let it grow, or you make it grow, then using certain criteria you try cutting it. So, this is what I was trying to say. Let us say this is a fully grown tree. Okay? Now, suppose we decide to cut it here after this A3. So, if we stop it here, this is our leaf node. Which leaf node I will adopt? The highest occurring leaf node. So, either I put it class B or I put a distribution like 2 by 3 times I am going to get class B and 1 by 3 times I am going to get class A. Either you put some kind of distribution actually counting the records, or you simply put it as class B. So, that by chance if something is erroneously detected as class A, it is eliminated. So, this is from a fully grown tree I have chopped off. Similarly, starting from root node, when I move ahead, I may decide to stop here. So, if I decide to stop here, again I will follow the same approach. What will be the class label here? Class A is appearing a number of times. So, my label will be A. Or I can also have a distribution where A is occurring with probability 2 by 3 and B is occurring with probability 1 by 3. I can also extract rules from a decision tree. How do I extract the rules? To extract the rules, if you remember while talking about the rule basis, rule usually has two parts, antecedent and consequence. So, this part before the leaf node makes the antecedent and this is your consequence. So, accordingly the antecedent, how many rules will have? That many branches. This is my first rule. So, this, if I follow this branch, I get my first rule. If the director is dir 1 and award is no, then likes will be no. If director is dir 1, award is yes, then like is yes. So, likewise I can now extract 5 rules. So, when this is a very small example, but when we have a large data set with many variables, we are going to get a very big tree. So, in that case we are supposed to get large number of rules. So, out of those rules, how many to select? So, while talking about rule based recommender system, we will also discuss in this line. So, these are the disadvantages of decision tree induction in recommender system. This is particularly not suitable for high dimensional data such as text. Making a tree is difficult and experimentally it has been shown that it gives poor performance. However, some of the very early applications, they show good utilization of decision tree, and moreover this is a very explainable method. So, therefore, as a first method we have discussed about it, but let me tell you, this is not a practical method as when we deal with a very large data set. We can use them to get the rules and use the rules after removing some of the redundant and not very useful rule and make the system faster. So, it has been observed that even rule based classifiers can provide superior result because they do not assume strict partition of the feature space. So, what do we mean by strict partition? Because you saw that as we move ahead, we started with the entire data set and each side of the tree, the data set was distributed. So, we have to follow only one path. So, if any observation comes which is not following any of this path, this is discarded straight away. So, such things can be avoided if we go for a rule based approach. So, with this we stop. These are our references and this is how we conclude. Decision tree, one of the simplest choice for content based recommender system if the number of features are less. Many early recommendation implementation use decision tree methods, but they are not widely adopted due to scalability issues. However, they are very explainable. Thank you.